It's very promising. I'm really looking forward to it.
Thank you.
And good luck.
Thanks. Cheers. So good boker, everybody. My name is Uri. Yeah, feedback is on. So I'm Uri Shaked. I'm a front-end web developer. My day job is I work part-time for BlackBerry. Yes, they still exist. And in my free time, I do a lot of fun stuff, which I'm going to tell you about right now. So these are the slides. I also, be quiet, Mr. Feedback. I also share them on Twitter, so you can find the link to the slides on my Twitter. It's going to be up here. I don't know if you can see the mouse. It's going to be up here for the duration of the talk. So let's start. My story starts about a year ago, or a little more, when I found this 3D printer on Kickstarter. And of course, I backed this printer. It came with a lot of promises. And I decided I want it. I want to have it. How many people in the audience have 3D printers? So it's fun when it works. But unfortunately, this Kickstarter project came with a lot of promises, but failed to deliver. The real story is that 2 years earlier, I ordered another printer from the same company on Kickstarter, and it was pretty much a failure. The software didn't work at all, and the hardware was pretty good. So in this new campaign, they said, we learned from the past mistakes, and we are going to do it so much better. And we are also going to open source the firmware and everything, and I believed them. Luckily, for the older printer, the micro 3D printer, the older one, there was some guy from the community who created an open source firmware and a better software, which made that printer work perfectly. So when I got my new printer, my M3D Pro, I was hoping for something similar to happen. And then I saw this comment on GitHub. Basically, it's the same guy who built the alternate firmware for the micro, the older printer, and he said, getting our firmware to run on the Micro Plus or the M3D Pro, that was my new printer, first requires figuring out how to decrypt M3D's official firmware. He also included a lot of information about how he did it with the previous firmware, and at some point here, he mentioned they used the substitution cipher. So anything funny about substitution ciphers? OK, perfect. Everyone should use it, and we're going to see why right now. So I said, OK, decrypting M3D's official firmware. Accepted, challenge. So I had this firmware, and I wanted to decrypt it. How would I go about it? I had 2 options. First of all, I needed to put my hands on that firmware. One option would be just to try to connect with the hardware with a microcontroller inside the firmware and extract it somehow. The problem is that it would void warranty, and there is a good chance I would destroy my firmware. So I tried to see if I could somehow get through the firmware update mechanism and extract the firmware from there, which was supposedly encrypted, as the guy said on the GitHub comment. So I tried to I downloaded the software, and how many of you know .pic? Not too many. Am I in the right place? Anyway, .pic is a nice tool that allows you to take .NET projects, decompile them. So I loaded their software, which was written in .NET, into .pic, and I found in one of their files this resources section, which included very promising files called M3D embedded firmware. I found 4 of them. They only had 3 printers. I figured out later why they had 4 here. After I extracted the firmware, we had a fun part of trying to figure out what kind of encryption they used and whether we can defeat it somehow. And this is what we are going to do now together. We are going to walk through the journey of decrypting this firmware. So initial analysis, you get a new firmware, you start looking at a file. First of all, it had no readable ASCII string, so obviously it was encrypted. I hoped maybe it would not be, but it was. The file size was 54 kilobytes, but when I tried to compress it, it was smaller. So this means this was not some kind of AES encryption, and that substitution cipher was very likely here. I also found another comment on GitHub saying that this was an STM32 CPU, which is ARM, Little Indian. I found the documentation for this CPU, which we'll see how it turned useful in a bit. And then I also found some mention that there are actually 2 firmware files, which explained why they had 4 firmware files in the software for only 3 products. So we are going to use both of these firmware files through our firmware defeating process. So the first thing I did was taking the file and trying to analyze it. Basically, I used Jupyter, which is a REPL for Python. How many Python reading people do we have in the audience? All right, so I am in the right place indeed. And Jupyter is a very nice tool used in the data science community. So let's open Jupyter, and I hope, can you see the code here? Is the font large enough? Please say yes. Yes, I get likes. If not, please move to the second row. So basically, I have here a little code that these imports we are going to use later that reads the firmware from the encrypted firmware from a file. And the first thing I did was simply to create a histogram that shows for each of the byte values how common they are. So we are not going to go over all the code. I will just explain what each block of code does so we can get to the exciting parts faster. So let's run this. And we can see this histogram, which has a very nice this spike in the middle. So there was one byte which appeared much more than the other bytes. One value that appeared much more. This is the value, the zoom is too large so we can't see it here, but this was 139. I still remember this. My guess was that this was null, this was 0. 0 is a very common value in firmware files because it appears in memory addresses, a lot of pointers. Every null terminated string is obviously terminated by null. So my first guess was that this spike that we see here, the most common value, 139, was actually 0. So with that in mind, I started creating a small table, let's do it together here, that maps 139 to 0. That's our first guess for today. Then I went to the firmware file and I started just, going over it. And then this is the firmware file, the encrypted one. And near the end of it, I discovered this 1F1F1F1F. I actually have a slide for it. So yes, you can see those 1F1F1F1F near the end of the firmware file. And my guess was, usually when you have firmware files, they are padded with FFs. Because of the way flash memories works, that's the best value for padding because it can be overwritten later. So my guess was that this sequence of 1Fs actually stood for FF at the end of the file. So with that second guess, let's update the table and say that 1F maps to FF, not FFF. And I already guessed 2 characters, 0 and FF, which were the easiest. And now I started like trying to explore the firmware, see if I can find any patterns. And interestingly, I don't know if you can see it here, but I have a slide for this. I found at the beginning of the firmware, so this 8B is actually 139 in hexa, which is the zeros. But then we have a lot of 24s. And by reading the documentation for the CPU, I found that the beginning of the firmware actually contains interrupt vector, which is just a list of pointers to functions that handle specific events that happen on the system. And I also learned from the CPU documentation that everything, all the flash memory, all this firmware is loaded to 0008. So there is a lot of repetition here, and I know these should be addresses that are mapped into the firmware code. So and this is 00, and this is a little Indian CPU. So my next guess would be that 94 would be 08. So this would be a legitimate memory address. So let's add this guess to the table as well. That would be 994 would be 08. And we have those 3 bytes we guessed. So let's check on our progress. We have about 1% of the firmware. And this was about 2 hours of work into guessing. And at that point, I was like, OK, there is this huge file with a lot of zeros and some other random bytes. How do I continue from here? And I had this idea. What if I look for strings, you know? But the thing is, you won't find the strings in the file. But if I knew one of the strings that is likely to appear in the firmware and it was long enough, perhaps I could find a pattern of repeating letters in that string. So before we see that, I went again to .pic and looked at the software that runs on the computer and found a file called firmware controller, which sounded really promising, where I found this unable to init hardware, check micro motion cable connection. And I took this string, and the first thing I wanted to know is how many repetitions I have in this string. So hoping that this string would appear in the firmware, I wrote the following snippet. It's a little bit long, but basically, let's run it. What it does, it creates this nice plot where you can see each star, each different height represent a different character, a different letter. So this one is above A, so the green one represents all the A, and we can see the A characters repeats 4 times. And basically, this chart visualizes how many characters are being repeated, the pattern of repetition of characters. So we can see there are a lot of repetitions, like these above the C, this purple one repeats 6 times, and then we have this O, the red one above the O, which also repeats like 6 times. So this string had a very distinct pattern of character repetition. So we know the spacing and how many times they should repeat. And with that in mind, we can write some code that will look for a pattern of this repetition and try to find a match. So I went ahead and let's add a new block, yes. And I crafted some code that would try to find this pattern. So this is the string again. And then I have this code that basically goes over the entire firmware and goes over the third string and tries to find a match to the pattern. And if it does, it's print, hey, I found it, and updates our table with the corresponding keys. So as you can imagine, I debugged it, wrote it, debugged it, ran it, and it ran no output, nothing found. But if you look at a string, it says micro motion cable, and micro was all their model. So perhaps this string was just not relevant for my specific firmware. They had the same software for all the models of this printer. So I went to look for other strings with a lot of repetition, and luckily I could find another one. That was repetier protocol, and you can see how many E's and O's and R's we have repeating here. So less repetitions, but still unique enough. So I said, OK, why won't I just copy-paste this code and try to search for it? And I copy-pasted the code, ran it again, and yet again, no match. So far, I spent like more than 10 hours trying to figure this out, and I only figured out around 1% of the dictionary for decrypting this firmware. But I decided it was not a time to give up yet. And I tried to look at the code that I used for the micro 3D. So the guy on GitHub posted the exact process that he used for micro 3D, and he also open sourced the code that encrypts and decrypts their firmware. So looking into that code, I actually found on GitHub, this is the code, and nothing is important here. I just want you to take my word for it. If we find the right line. So yeah, this is the line that actually does the description from the table. And what you can basically see here, this little expression basically swaps any pair of adjacent bytes. And take my word for that, we're not going to spend time on that. So in the micro firmware, they swapped any pair of adjacent bytes, and I wanted to see maybe that was the part I was missing. So I went back to my Python, and I added another method just before loading the firmware that would just swap the pairs of bytes. So let's go over this. Let's run this method. And if you are a really quick Python reader, you can identify this expression from the C code that we saw earlier, just written in Python's way. And let's run this and run this. So now we have reloaded the firmware, but with every pair of bytes swapped, just like they did with the micro. And I prayed for the gods of the encrypted firmwares and run this code again, searching from unable to init the hardware blah, 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 blah. No, not that code, the one below. So I ran it again, and it found it. So thank you, first sign of progress. And since I already copy-pasted the code with the other string, I also ran it, and it found it as well. So I wrote another method so I could easily measure my progress, and I obviously called it progress. So we have 8% of the firmware figured out. And, another thing I want you to notice is that the offsets for these two strings is 48 something, and this is also 84 something, and this is also 48 something. They are both very close. So I figured out this part could probably be where they have the strings. So the next step for us would be to try to look there and try to see if we can guess some of the letters there. So I wrote a small hex dump method. Some of you can probably recognize these escape characters that will put colors in our hex dumps. And I will show you in a moment what this does. Let's run it first. So this is our super powerful hex dump. And we are going to try to dump the area of the string and make some guesses. So that would be first ASCII. And now you can see the output of this hex dump. And as you can see, it prints the bytes that we already know. And for those we still don't have the translation, it prints them in purple. So we can easily tell the difference between bytes that we already know and bytes that we do not know yet. And by looking at these strings, we can make a few wild guesses here. Like this firmware name, you could probably guess what the first letter would be, right? Yeah, shout it, shout it. You're right. So let's update our table, rerun the code, and we can see it says firmware name, firmware Arian, any ideas? Yeah. I just need to copy-paste this correctly. So we have this. Say it louder. I couldn't hear the S. It sounds like F, but it's an S, right? Actually, no, this is V. That's OK. That one was incorrect. And that would be the 23, I guess. All right. So we have this guesswork. And now it reads firmware version. And we also have machine type. Why? I also asked myself why. Why am I doing this to myself? I don't know. Anyway, so type. And then I took the liberty so we can see serial number, which is another string. And this gave me the confidence we are going through the right path. And we also have this M-D. Yeah, 3. That's right. So let's put there a 3. That would be 60 something. So that would be a 3. And then talb is not good. You only want a table. OK, so we have M3D underscore P something. And since the name of the product is M3D Pro, I would guess that these two characters are R and O. So let's try to add them as well. So 40A and F5 would be for R and O. And by the way, thank you for helping me. I love that we are doing this together. So at this point, I took a few guesses, and I have most of the letters. And it starts to look promising, like we are onto something. So I went over both firmwares, and I was looking for even more ASCII regions with ASCII characters when I found this nice thing next to the end of the second firmware. And as you can see, it figured me out a lot of characters. We are not going to do them by hand. But basically, this is what I saw when I started. H-E-O-B-O-E-D. Any guesses? OK. So I started by guessing that this B-O-R-D would be bored. So I guessed A and D and made a lot of other guesses, which revealed this string said, hello, board. Hi, nice to see you today. Try D. And then it was cut. I really wanted to know what I needed to try, so I tried to Google it, but no results. If you know where this comes from, I would love to learn from you. Anyway, with that in mind, I went and looked for more ASCII, and I found a few more regions and a few more strings that I added to my dictionary. And at this point, I even found %. And at this point, I was pretty happy. I typed progress. And we are only almost 20% just by doing some guesses. We got 10 more %. So where can we take this next? We are I scanned the files a few more times. We were out of ASCII strings. So I started looking for other patterns when I found this mysterious table. I found in the smaller firmware some offset where I had an interesting pattern. Let me show you this. So this would be the mastery table. And you can see here, this is a table, and it has this CE, BB, LO, BTY, WY. And this is an ascending sequence of letters. And then we also have an ascending sequence of lowercase letters. And at this point, I said, OK, I have most of the uppercase letters. So let's check which letters I'm still missing and try to figure out if I could just put them in the missing spots. So I wrote another small snippet that would go over the table that we built so far and look for all the ASCII letters and prints the ones that are missing. And we have only a few missing letters. We can see we have G and J, Q, X, and Z. So we have CE, something, something, L. And since the only letters we don't know are G and J, and these are also the only letters from this list that happen to be between E and L, and we assume that this is actually an ascending sequence, we are going to make another guess and say that these are G and J. And let me see, so this was G, 95, and J would be just next to it, 27. So that would be G, and that would be J, and I have a little OCD, so excuse me for that. And then we have LO something T, and the only letter we are still missing are Q, X, and Z, so that must be Q. So again, table position, what was that, E8, 0xE8 equals to Q. And then, just to run it again, we have this nice sequence. I did the very same process with the lowercase letters, just trying to deduce what letters we could have. And we're not going to repeat it right now. I'll just write the result. And we had this nice sequence. There was one letter here I couldn't figure out because we had both. Let's update the list of missing letters. We had both P and Q, which are next to each other, so I couldn't guess which one would fit here between M and S. And at this point, I was looking at the beginning, and I found this interesting pattern where you have 0, 0, 0 a lot, then something, 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 a lot of repeated bytes, and then 8, 8, 8, which we figured out at the beginning. So I thought to myself, perhaps this would be 1, 1, 1, 2, 2, 2, 3, 3, 3, etc. Perhaps this is, again, ascending sequence. And I just tried to match, and there was 7 different values between here and here. So it seemed like a good match. So obviously, I updated the table with these guesses as well. And let's print this again with the new guesses. And it seems like a good match. So we have the start of the beginning of the double table. We have some values at the beginning of the middle of the table. And it seems like it's some sort of curve represented here, because we had this value 0 repeating for a lot of times, and then we had a few ones, less 2s, less 3. Like, it seems to reduce the number of repetitions. And then in the middle, we have every other letter or so appearing in this table. And near the end, we can also see FF and a few more repeating characters. I could try to do more guesswork and try to interpolate the values in the sequence, but I decided to turn to Google at that point and to Google this string, hoping Google would open. Of course, I do all my searches incognito, hoping I would find something, and I indeed found this string in a lot of the results. But if you look closely, you will see it looks promising, but then the lowercase letters are ACF or ADF, and I had different lowercase letters. So it looked promising, but I couldn't find anything that matched the other letters I had in this table. So I ran a few more searches. I tried to search for the lowercase letters, and then I tried to search for, the hex values. Maybe they are represented as hex values. So running this hex value search with quotes, so I'll find exact matches. And basically, I found, do you like riddles? But it's not the riddle I was looking at. When it occurred to me that if I just add 0x before each of the characters, each of the hexa numbers, I may have a better chance. So I Googled it. Correcting nonlinear brightness LEDs. Interesting. The printer had an LED that was blinking, like fading on and off, and this seems like this could be something useful for the firmware, and it's from Electronic Stock Exchange, so it must be legit. Trust me on this. So I opened this answer and started to look, blah, 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 blah. And nice, this is a curve, and I was expecting to find some curve. And here is a table. Here's the full set of 256 levels that I used. So somebody posted an answer how to control the brightness of the LED on Stack Overflow. So I was really pumped. I just copy-pasted it into my Jupyter notebook. Let's close this incognito thing and paste it. So I just copy-paste the entire table, and I wrote a little snippet of code that would just go over each of the bytes, try to match them with the bytes on the table. If this is a value that we already know, we already have it in our table, we compare it with what we expect to find there, and if it fails, we die miserably with an assert. Otherwise, we just update our table. And to my surprise, I ran it, and we had a perfect match. So, time to check on our progress. And we see we have 70% of the firmware. We are getting there. I love this. At this point, I started to develop new hope. So I found this mystery table, which turned out to be the controller for the brightness of the LED. And then I Googled it, I found a table, and we saw some light at the end of the tunnel. And then I went to look for other patterns in the firmware, where I found another table. So let's have a look there. That would be the second table, right? So I found this table, and you can see there is like this nice column here, which read 3C, something we don't know that repeats a lot of time, 3E, and then something we don't know again. So a wild guess would say that if this is 3C and this is 3E, this would probably be 3D, like the printer. And this one would be 3F. And I also had another guess that since we had another column here that started with 3C, but it had this 22, it could be 3B, the value before. So I ran these guesses, and now with these guesses, the table looks like 3B, 3C, looks legit. And at this point, I was started to wonder what the other values could be represented. Like it's group of 4 bytes. Actually, it's Little Indian, so we read it this way. These are groups of 4 bytes, and they seem to be increasing. That when I tried to convert it to a D word, it didn't mean a lot to me. I would like seeing an increasing sequence with some difference between the numbers, but they had no meaning. And then, could you guess what it could be if it's not D words? Floats. So I had another guess. This might be floating point numbers. So I wrote a little code. I basically just copy-pasted some of those numbers, like this one, from the sequence. and tried to ask Python to print them as little Indian floats. And I found out these were all floating numbers between 0 and 1, and they were increasing. They were in ascending sequence. So it seems to be like a function that goes between 0 and 1. And in order to know what this function looks like, I decided to plot it. So I wrote a little code snippet that would just go over this table from the floats offset in jumps of 4, go over each set of 4 bytes, see if we have all of them in the table. If we could find translation for all of them, we would just add them to an array. Otherwise, we would put a none. So we'll have a plot with all the points that we know and spaces where there are points we don't know. So I found this table. I figured out this could be floats. And now I'm going to try between 0 and 1. And now I'm going to try to plot them to see what it looks like. Oh, I have 10 minutes. I thought I have 7. Thank you, Inbar. So I can breathe and take a sip of water. Before we plot these numbers, I love Python. So this is the numbers that we found. It's indeed an ascending sequence. It seems like another kind of curve. Why am I wasting real estate on the address bar? I don't know. It seems like a real nice curve. And at this point, I was like, OK, I have those points. I have the missing points. It's Python. It can help me find the missing points. And I remember there was a way to interpolate. If I have a function, I could interpolate. But to be honest, I'm not too much into data science, so I turned into 2 of my friends. I can't see if they are here in the audience, Avi Aminov and Yoni Rosenshine, who are more into math and data science. And they told me, yeah, there is this package called SciPy, and it has this amazing function called interpolate, which can take a list of numbers with some gaps and fill the gaps, just what we need here. So for another snippet called interpolate, basically there is this interpolator that builds the list of the points that we already know, their x values and y values. And we called SciPy interpolate interp1d, which should guess, create a function that guesses the gaps. And then we plot the original points and the interpolated points. So the interpolated points will be yellow, and the original ones will be green. Let's do this, and just to see if it guesses well. And these are the interpolated points, the points that Python guessed for us. Can you see the difference between green and yellow? Yes, yes, like. OK, let's actually make it even easier. Yeah, let's change these ones to an x. So we have all these guessed numbers. Now, since these are floating point numbers, and these are just guesses, we could be off by like 1 or 2, because these are just guesses, and floating point is not super accurate. But I tried to, so we know the most significant byte of each of those numbers. These are like this 3E, 3F, 3D, and 3B that we guessed. And we want to fill the gaps in the second most significant byte. So even if there is an error, there is a lower chance of an error in the more significant bytes. So basically, I wrote another snippet of code that we are going to run now. And that snippet of code we already run that. We'll try to predict the missing values for the second most significant bytes in places where it's still missing. And basically, it just takes, it goes over the points. We are only going from the 10th point, since we can see that at the beginning, we only have 2 data points, and the curve is kind of high, so there is a better chance of errors. So we just try to interpolate the values between this point and the end of the curve. And basically, we're trying to see whether our predictions match the actual bytes there, just to check how close we are, how close our predictions for bytes we already know. And then for bytes we don't know, we just update our table with the prediction. So let's run it. And we are trying to predict the second most significant byte for each of the firmware bytes. And this had no errors, which means that, thank you, Inbar, which means that we still have 5 minutes to do the next byte, amazing, which means that all the predicted values match the values that we already know. And for some of those values, these values that did not appear in our original points array because they had other bytes missing. So this is a good signal that our prediction function works well. And we also fill the table even more, so now we are 85%. It feels like we are almost there. I think we are also up 85% of the time, so that's a perfect match. So the next thing would obviously be to do the same. Let's update the plots. Let's plot them again. So this is now with the new bytes that we predicted. They are already in the table, so we already see them on the plot. And we can update our predictions as well. And just a moment, let's run this one again. So, yeah. So we see a lot more green and less yellow. And we are going to do the same now with the third most significant byte and hope we still get a good amount of matches, even though the precision drops as we go to the least significant bytes. So running the same snippet again, and again, and again, and again, predict missing bytes. But this time, we are going to go 1 byte back to the byte number, the second byte. It's little endian, so the most significant is 3. Next is 2. And now we're going over byte number 1. And here we see that there was one error that could be expected because the precision went less, but we spotted that we already had a translation for the value that we guessed incorrectly, so we just skipped that one. And we see that we have 98% of the firmware and no other errors. So we are probably doing good at our guesswork. And at this point, I felt like we are still missing 20 values. And that would be a good time to stop doing data science and look for patterns and actually try to look at the code. So I opened IDA, and I wrote a little script that would go over the disassembly. And whenever it found a line which had a missing bytes, it would color it red. And then I created a keyboard shortcut that would allow me to cycle through the possibilities, because we only had 20 possibilities to fill in. And after about 3 hours of finding small functions, trying to figure out what they do, I mean, with this function, you can see it loads something into R1, and then it compares R1 to 0, and then it does something. And then the missing byte obviously doesn't make a lot of sense here, where we compare R6 with where we load something into R6 because we don't have R6 mentioned here. And the next thing we do is compare R1. So there would be much more sense to have some opcode here that would do something with R1, that would load a value into R1. And going through all the 20 possibilities, I found only one that loaded something into R1, which was that one. So I did this until I figured out the rest of the missing 20 bytes, which finally revealed the secret of the firmware. And the end of the story. So key takeaways when we wrap up. When you are doing such a thing, look for patterns. Everything I found here was just because I found some patterns that caught my eyes, and I decided to dig into them. Use data science tools. Python rocks. It helps. It's hard and frustrating, so don't give up. Thank you.
Wow.
Thank you.